So this talk is going to be on polynomial formula for sums of powers of integers. So, for example, if we define by Snk equal to summation j to the power k, j going from 1 to n, where you fix positive integers n and k, let S and k be this. Then there's a theorem, there exists a polynomial summation akr n to the power r equal to 1 to k plus 1, 1 to k by k plus 1 equal to S and k. That's a theorem that I would like to prove. In your high school days, we know about Sn1. In fact, this formula goes back to the great Gauss. Gauss, when he was in elementary school, his teacher wanted to have a cup of coffee. So she or he gave this problem of summation j equal to 1 to n. Find an expression for Sn1. Sn1 is equal to this. And he very quickly solved this problem and was very quiet after that. Namely, if you write say is equal to 1 plus 2 plus 3 all the way up to n. That's what that sum is. But then, since the real numbers are commutative, you can write in reverse order. The sum is the same. So it is the same as n plus n minus 1 all the way down to 1. If you add the 2, then you get 2 times Sn1 is equal to n plus 1, n minus 1 plus 2, n minus 2 plus 3, and so on. All of them are n plus 1. So it's exactly equal to n into n plus 1. So implies Sn1 is equal to n into n plus 1 by 2, which you can rewrite as n squared by 2 plus n by 2. This is Gauss's proof. But it uses the crucial fact that the real numbers are commutative. If I were to force you, then you'll have to give a proof of the fact that the real number system is commutative. And that's not so easy to prove. But if accepting the commutative property, this follows. This is one formula. And then, if you look at Sn2, which is 1 squared plus 2 squared, all the way up to n squared. And then Sn3 equal to 1 cubed plus 2 cubed, all the way up to n cubed. In high school or in college, I don't know where it's offered, we are asked to give a proof of this formula, explicit proof of this. The formula is given to us, and then we have to verify this through the principle of induction. But then, I want to give a proof of this theorem without using the principle of induction, a direct proof. This is what we have given, that is one, Kothari and myself have done it. So, this is Sn1 is equal. Then in high school, or I don't know where it is done, in high school or in college, I don't remember, somewhere. College, pre-university, okay. This formula is given, and you give a proof using induction, the principle of induction. What is the principle of induction? It says that you have a collection of propositions, P of 1, P of 2, P of 3, P of n, P of j, and so on. So, let me explain this principle of induction, using induction. Let P of n equal to 1, 2, 3 be a collection of statements. Let P of 1 be true. So this I call it P of I, principle of induction. What is the principle of induction? Is the following: let P of 1 be true, and then take the hypothesis, let P of n true imply P of n plus 1 is true. So if these three things are available to you, then the conclusion is that P of n is true for all n. All integers n are equal to 1. Now it turns out that this principle of induction follows from the greatest lower bound property of the integers. It's crucial that you can prove this principle of induction as a theorem from the property imposing on the integers, namely the greatest lower bound property. So let A be the set of all n, so that P of n is not true. Consider the collection of, we want to prove that A is empty. We know already that A does not include 1. So, since my hypothesis P of 1 is true, A is bounded below by 2. And the real number system or the integer system has a property that any set that is bounded below has a greatest lower bound. So, sorry? Well-ordering principle. By the well-ordering principle. So, well-ordering principle is also an axiom. You have to start somewhere. So, assume well-ordering principle is given to you. So, you have to use the well-ordering principle. Well-ordering principle, property of capital N equal to 1, 2, 3. So there is a fundamental axiom in mathematics: every set can be well-ordered. That's Zorn's lemma. Yes. So you have to grant that to me, otherwise I will be in trouble. Piano's construction also assumes that piano's postulate, So, but the well-ordering principle is every set can be well-ordered, is Zorn's lemma, and you assume that the natural order in which we have the integers, piano postulates, gives you the well-ordering property. Yes. So we have to start somewhere. So, by the well-ordering property of n, A has a GLB, greatest lower bound. Call that C. Then C has to be greater or equal to 2. But then C minus 1 is not in A. C minus 1 holds. P of C minus 1 holds, but then by the principle of induction, if P of C minus 1 holds, P of C holds. So that's a contradiction. So then then C minus 1 does not belong to A, and P of C minus 1 holds implies P of C holds, i.e. C belongs to A. C is not supposed to belong to A, but we have concluded C belongs to A. There is a contradiction, and therefore this thing holds. A contradiction. So, the well-ordering principle gives you the principle of induction. So, in principle you can prove it, but I want to prove it without using the principle of induction. That's what is contained in this paper of mine. So, we want to prove this theorem, theorem 1, without the principle of induction. So what we are claiming is that this S and K for any two possibilities n and k is necessarily a polynomial of degree k plus 1 in n. For example, if we know that Sn1 is n squared by 2 plus n by 2, polynomial of order 2. Sn2, for example, we know from high school days, this is equal to n into n plus 1, or did you say pre-university? High school or pre-university? Somewhere. Yeah. N plus 1 into 2n plus 1 by 6. Yes. And then Sn3 is going to be equal to n into n plus 1 by 2 quantity squared. All of them we were given the formula, we were asked to prove it by induction, which we did. We were very dutiful students, so we did that. But now I'm going to give a proof without using the principle of induction, directly. And that's as follows. So we'll give a proof without use of principle of induction. Remember, the principle of induction has three statements, namely, let Pfn be a collection of statements, Pf1 be true, Pfn true implying Pfn plus 1 is true, then Pfn is true for all n. So I don't want to use that, because that you require the well-ordering principle, which is all right. But here we give the following proof. So we notice, call this f of n, f of k comma n, let's say, k of n. Fk of n is equal to this. Then we'll verify there exists a gk of n is equal to summation akr n to the power r equal to 1 to n plus 1 will satisfy n greater than or equal to 1 and k greater than or equal to 1. We'll verify that gk of n plus 1 is equal to gk of n, so this is up to n, sorry, plus n plus 1 to the power k. So now we will show that there exists akr with this property. Okay? And that we will do that as follows. So what we want is that these constants akr are equal to 1 to k plus 1, or equal to 1 to k plus 1, satisfies this equation, gk of n is equal to that. So we notice that summation akr n to the power r equal to 1 to n plus 1 is equal to n plus 1 plus n plus 1 to the power k, r equal to 1 to n, is equal to summation akr into n to the power r equal to 1 to n plus 1. If you notice, fk of n satisfies the same equation, and we want to prove the uniqueness of the solution of this equation. And then, all that we have to do is to equate the constants. If two polynomials are the same, then they will be identical even only if the coefficients are the same. So using that property, I am able to prove the following fact, namely, I identified explicitly what the constants are. let me write down the constants. Let me write down explicit formula. So I'll write down the formula and then I will switch on to another subject. So just using that fact, here is S1n. We already know it is n squared by 2 plus n by 2. S2n, which is n into n plus 1 into 2n plus 1 by 6. If you simplify this, it will be n cubed by 3 plus n squared by 2 plus n by 6. S3n equal to n to the power 4 by 4 plus n cubed by 2 plus n squared by 4. Then this is all well known to us from our high school days. Now comes the new thing, S4n. Remember, S4n is what? Is the sum of j to the power k, j to the power 4, j equal to 1 up to n. And that is explicitly equal to n to the power 5 over 5 plus n to the power 4 over 2 plus n to the power 3 over 3 minus n over 30. That is Sn4. And then S5n, that is, what is S5n? Remember, Skn is simply equal to, oh, I wrote it wrong, Skn. The summation j to the power 5, j equal to 1 up to n. So this is equal to, well, but I'll write down what is explicitly the impression is. N to the power 6 over 6 plus n to the power 5 over 2 plus n to the power 4 over 4 times 5 over 12 and then plus n by 42 plus n squared by n squared, sorry, this is wrong. I wrote down the wrong number here. N to the power n and minus n squared by 12. S6n is equal to n to the power 7 over 7 plus n to the power 6 over 2 plus n to the power 5 over 2 minus n to the power 3 over 6 plus n over n over 42. We computed this S6, S7n, S8n, S9n, S10n, S11n explicitly, and also all the way up to S12n. In our paper, the following are computed explicitly. Basically, the theorem is the following, that S and K equals this polynomial for some appropriate coefficients AKR, and we have computed explicitly what these AKs are. So we have in fact completely solved the problem for any integer n and any integer k. And I wrote down the formula for up to S12n, I say S6n, but in this paper I have all these formulas explicitly available. So let me give you, so in principle, you can, without using the principle of induction, it is possible to derive an explicit expression for Skn, and we have computed up to S12n, and then we have the following conjecture. So this is a conjecture. Show, well, conjecture is that AK k minus 2r is 0 for all r, for all k, greater than or equal to 2r plus 1, k and r integers. We don't have a proof of that, but we have verified it for a number of cases. So this is an open conjecture. Let me give you one application of this idea where the SKN show up in a natural fashion. So let me write that down. Application, for an example. Let Sn be equal to 0, 1, 2, 3 up to n. Be a finite set. Question: how many intervals I comma j, I and j belong to Sn, I less than j are there? So Sn is a collection of integers 0, 1, 2, 3 up to n, and I look at any pair I comma j where I and j are integers, and now consider the total number of such intervals that you can generate. Well, if you consider the interval of length 1, there are exactly n plus 1. There are exactly n of them. 0 to 1, 1 to 2, n minus 1 to n. If you consider the intervals of length 2, then it is 0 to 2, 1 to 3, and so on and so forth. So you can show that the total number of intervals, answer, the total number is exactly n into n plus 1 by 2 equal to Sn 1. And now you can ask question 2. Is you take an integer lattice 0, 1, 2 up to n, and then 0, 1 up to n. Consider this n by n squared. And how many elements are there? N plus 1 times n plus 1 elements are there. And the question, how many squares with integer coefficients with I comma j belonging to Sn are there with sides parallel to the axis. The answer is that the number of such squares is exactly Sn2. The answer is Sn2. And then similarly you can answer the third question. How many cubes are there with sides parallel to the axis and lying in the integer lattice? And Sn3. Those are not easy propositions to prove, and the reference to them is the following. Oops. So, reference with the KBA and Escotari resonance, August, pages 726 to 743. In the month of August, two years ago, 2015. So you can find a full paper in that one. It has listed all sorts of problems. Then, the next I want to, is there time now? Okay. I want to talk about the following problem. So this is an explicit formula for Sn2. There are several proofs available. We have given two proofs. By the way, the formula for 1, 2 and 3, k equal to 1 and 2 and 3 was given by an Indian mathematician by the name Aryabhatta in the form of a Sanskrit shloka way back in the 12th century. And that was what Shailesh Shirali told me. I have not verified it myself, but I can give you a reference to the work of Aryabhatta. Translation of Aryabhatta by Walter Eugene Clark of the University of Chicago Press in 1930 already. Okay, here is the second problem that